Hello, everyone. Thank you so much for joining us today. Today is actually officially kickstarting our ZK month. The previous week that we had sessions was week 0, and we had cryptography-based sessions. The idea was to ramp up people, in the space of cryptography. We also actually have another interesting cryptography session tomorrow, which is on ECC and SHA 256. And we may have some intermittent, some intermediate sessions as cryptography sessions. And these will be more deep dive sessions, probably a little bit more mathematics. So for those who are interested, there will still be some cryptography sessions. But last week, 0 was basically just to brush up on cryptography. And we start our ZK month officially today, which is the 2nd of October. And this is our first session, which is an introduction to zero knowledge proofs. I'm super excited to have Sweta as one of the speakers. Sweta has been a mentor for a lot of folks with the Phoenix Guild, and she has been an inspiration because she herself started working in the Web3 space a while ago, and she has made huge leaps and strides in this space. And yeah, I'm so glad that today she's able to come and talk to us about this interesting topic called zero knowledge proofs. Shweta is a lead engineer and takes care of developer experience with Reclaim Protocol. She will probably talk about Reclaim Protocol a bit during her presentation as well, if you're interested. And they are also built on the idea of zero knowledge proofs. Welcome to the ZK month. This is going to be a month-long series of events which consists of a cryptography refresher, introduction to zero knowledge proofs. We'll talk about snarks and starks, and we'll also talk about a few protocols that are based on zero knowledge proofs and what are these different types of protocols doing. Some are talking about scalability in the Web3 space. Some are talking about privacy in the Web3 space. Are there any other interesting use cases? Maybe identity. We'll have talks about these different use cases from speakers from different backgrounds. About the Phoenix Guild, the Phoenix Guild is hosting the ZK month, and all of the sessions will be online. The Phoenix Guild was started in early 2022 with the idea of bringing more diversity in the Web3 space. What we offer is education and mentorship. As we are doing right now, we have workshops and boot camps that run throughout the year. We aim to create inclusive events where inclusive events where people feel comfortable at home in learning things from scratch. Right, Web3 can be very overwhelming for a lot of people, and we want to make sure that we are able to include everyone to this in this space. We have about 13 plus chapters in India, and we have a chapter in Malaysia. And we are setting up more regional hub across the globe where we are going to train these folks, the leads, the directors of these regional hubs, so that they can mentor and this entire education in Web3 can become a scalable concept altogether. We work with different protocols, different organizations to provide opportunities. These could be anything between being able to network to being able to get a pass to an exclusive conference, being able to get a job, being able to be a part of the accelerator, being able to get admission into different hackathons and things like that. So opportunities come in a whole lot of ways, and just keep an eye out for them. Whatever suits you, you should just grab it immediately. Our mission and vision is to create and onboard the next million diverse builders in the Web3 space. We want to make sure that when you're looking at leadership, you see that there are different kinds of people who are present at the leadership, who are representing maybe folks from tier 2, tier 3 cities in various countries. We are looking at women, we are looking at non-binary folks as entrepreneurs, senior engineers, and we want to enable through this idea of education and mentorship, we want to enable these folks to be in these spaces. This is a few of our partnerships. We have worked with a lot of different protocols, and we continue evolving, working with different companies, different protocols as we go. And yeah, we have a global Telegram group as well as local WhatsApp groups for different chapters. You can join any of that if you wish to. And then we have a Twitter that you can follow. Thank you so much. And over to Sweta now, who's actually the host of the session. Let's go. Shweta, you're on mute.
Sorry again. So, hey, hello everyone. How are you? I'm really proud, and like I really appreciate this ZK month concept, and this is really needed, because right now if if someone is not aware of zero knowledge, we are really behind. So like moving forward, what I can see is like all the major applications will slowly move to zero knowledge proof systems, and maybe we won't know ki inside under the hood we are using zero knowledge, but we will be using zero knowledge. So it's super important to educate ourselves on zero knowledge things. So I'll just share my screen and get started. Just a minute. Okay, let me present my screen. Cool. Where is it? Okay. Yeah, so everyone can see my screen.
Yeah, I see it, Sweta.
Cool. Yeah, thanks. So today we will be talking about zero knowledge proofs. Basically, the basic agenda is to know about what are ZK proofs and existing problems, what are the existing problems, and how zero knowledge proofs helps us in solving those problems. What are the key properties of zero knowledge proofs, the types of zero knowledge proofs that exist. We will be talking a bit about snarks and some hands-on ZK that we'll be having. So this entire session that we'll be having today will not be focused on like mathematics, because personally I feel that we should, if we do back engineering that way, it is easier to learn. As in, first we should know. Okay. So first we should know about like how things are happening at a very higher level, and then we can gradually dig under the hood, like how things are happening. That will, for example, like in the entire ZK month you will get to know how things are happening under the hood, maybe more mathematics. But I would limit this presentation today to more on the higher level side, so that everyone first of all gets onboarded on like how ZK proofs exactly like are made of, and what are the high level concepts around it. Cool. So let's get started. So first of all, there is a need for privacy and secure communication. And why do I say that? Okay. For example, suppose, there's a bar and you want to go. Maybe you're so happy about it. Yay, we'll go to the bar, booze. But there's a policeman, like, bouncer or some like the security people there, and they ask you verify your age, show me your ID. What do you do? You show them your Aadhaar card or like some social ID. But then when you show them your social ID, you not only reveal your date of birth, but your entire information, other information, maybe your name, your address, and all the other information, which might not be needed. I think I'll mute.
Yeah, Shweta, can you give me controls to be co-host? You
Yeah,
can
yeah,
go
yeah.
admin TPG and make me the co-host.
Yeah,
So
yeah, sure.
I will be able to mute everyone then.
Yeah.
Sorry. Yeah, okay, perfect.
So yes, so now when you share your Aadhaar ID card or like any other ID, like government IDs, you not only reveal your like date of birth per se, but you also reveal your other information that is there in your ID. For example, your address, your name, and not to deny there, like why should you share your maybe full name or your address? Like that is not required, right? Just to prove that you are above 18 years, or just to prove that you're more than 21 years. Okay, so it's not needed even to just reveal your date of birth. You should be able to say, like, proof to the officer that, hey, I am, like, take my proof, verify it, and I am sure shot more than 18 years of age or more than 21 years of age. Okay, so that is where zero knowledge proof. So this is just one example. There are like a lot of other examples in the blockchain ecosystem as well. For example, most of the blockchains are public blockchains, where all the transactions that are being done is publicly visible. Okay, so for example, I do not want personally, like, to like someone to know what transactions I have done. I should just have a proof. I should be able to show a proof that yes, I have done some transaction, but I am not willing to share this information to everyone. I should be selective. I should be, selective in who should I share my information to. And that is where zero knowledge proofs come in. So what is zero knowledge proof? So it allows one party to prove to another party that they know a specific piece of information, like some secret key or password, without revealing any details about an information. For example, if I can prove to Gyan that I know the password to a lock without revealing the lock, like maybe combination itself. I can just prove to Gyan. And how is that? How am I able to prove to Gyan, or how is Gyan able to accept that proof, or how is Gyan able to verify that proof? Is because of zero knowledge proofs. So, for example, there is a colorblind person. I know this is a very cliche example, but one of the easiest way to understand zero knowledge proofs. So, for example, see, there's a person who is colorblind, and there's a person who is not colorblind. So, for this person, both these balls are of same color. She's saying, hey, no, don't believe you if you say that one is of yellow and one is red color. But the prover, that this person says, hey, no, you're wrong. These two balls are of different color. So how does this, so she's blind, she's colorblind, she doesn't know what colors these two are. So how does prover prove that these two balls are of different colors without even revealing the colors of the ball? Okay. So what she does, okay, they agree, they form a trusted setup. Okay, they form a trusted setup. Under this trusted setup, verifier, like she takes the two balls behind her back and tries to swap the balls and checks to the answer, like questions the prover if the prover is able to identify that she had swapped the balls or not. Okay. Now the first question is, did I swap the balls? The prover said no. Okay. Verifier is like, okay, that is true, I didn't swap the ball, but this might be a sheer luck, like he just guessed it and he's right. Okay, let's do it once more. So she did once more. This time she swapped the balls, and now she's asking, did I swap the balls? The prover said, yes, you did. Now verifier is like, oh yeah, he is correct again, like yes, I did swap the balls. So then she is assuming, okay, maybe this time again it is luck, like this is just a guess. Okay, so she said she's thinking, okay, fine, let's ask again once more time. Let's repeat the same, interaction. Now, third time, she asks again, did I swap the balls? He said, no. Verifier is like, yes, he's again correct. That means he might know, like that means he might, what he's saying that the two balls are of different colors, he is rightly able to pick that up. Like he's directly able to identify that the balls are of different color. He's right. So now verifier is able to trust the prover that what he's saying is correct after certain number of times the questions she asks these questions, like few questions to the prover. So is everyone on the same page until now? Like is everyone able to get like what did just happen? Like if everyone is with me, just put a yes on the chat, like yeah, so that it doesn't sound like if I am just going on repeating like or saying something. And yeah, cool.
Lots of yeses. So
Yo,
don't.
awesome. Yeah. So fine. So what we saw right now is a kind of an interaction. A trusted setup was built between the prover and the verifier, where both agreed to perform certain actions. The verifier will ask some questions to the prover, and prover will answer. Based on prover's answer, the verifier will come to the judgment or conclusion that yes, what the prover is saying might be correct. And here prover was not able to here prover didn't reveal the color of the balls. Without revealing the color of the balls, the prover was able to prove that the two balls are of different colors. Now, what should be the properties of zero knowledge proofs? Like that every proof to must satisfy so that it can be called a zero knowledge proof, right? Not any, so someone will come to me or you and say, hey, this is a zero knowledge proof of something, take it and verify it. But you cannot just accept any proof as zero knowledge proof. You should first check that if this proof satisfy these particular properties. And what are these particular properties? These are the three properties of zero knowledge proofs: completeness, soundness, and zero knowledge. Now let's see what these three properties really mean. So first is completeness. So what does completeness mean? It means that if the statement that is being proven, okay, is true, then an honest prover will always be able to conceive a verifier of its truth. For example, in our setup of, the swapping of balls setup, the prover who is honest, like no matter what, like how many times the verifier is swapping the balls, the prover, if they are correct, if they are rightly able to judge the color of the balls are different, they will be able to convince the verifier that they know that color balls are of different colors, okay? Because every time they will be answering the correct questions. So whatever question the verifier will be asking, the prover will be always be able to prove the answer in a way that will convince the verifier that the prover knows the answer. Okay, so that is called completeness. That statement will always be proved to be true by an honest prover. Next is soundness. What soundness mean? So soundness means that if the statement is false, okay, if the statement is false, no prover, no matter how clever they are, how what all like tricks and techniques they apply, they will never be able to convince the verifier that it is true. Okay, for example, in this setup, the ball swapping setup, there's a possibility that the prover might, so if they do not know they do not know if the balls are of different colors, there can be a few questions that he might not be able to answer correctly, that he might not be able to answer correctly that the balls were swapped or not. That way the verifier will get to know that the prover is trying to deceive, they are not telling the truth. Okay, so a verifier should not accept the proof if the proof is not like false. Okay, if the statement is false, the proof generated using that should all, like verifier should not be able to accept that proof. Next is zero knowledge. So now comes the zero knowledge. Why is zero knowledge with proofs? Okay, so what zero knowledge means? It means that the proof that will be submitted by the prover, it should not reveal any information about the truth that the prover is trying to prove. Here, the prover was trying to prove that the balls are of different colors, but he did not reveal the exact values of the colors, like they are red and yellow. Okay, so even without revealing the entire like actual information, the proof should be able to prove that information. For example, in the case of age verification also, for example, if I am trying to share a zero knowledge proof with someone to share like what age I am, for example, I'm greater than 18 years, I should be able to do it without even revealing my date of birth. That is what is zero knowledge. Like there should be zero leakage of knowledge of the exact value. Cool. So is everyone on the same page? Should we move ahead? If anyone has any questions or any doubts, or if I should move ahead, please comment in the chat.
Does anyone have any questions on like any of these three properties?
Yeah.
Have you understood? Because this will define, going forward, this will define a lot of applications that you'll build on top of zero knowledge. Okay, there is a question. Yeah, Sweta, there's a question from
Yeah.
Atul. Are
I
you?
want to know that there is an admin and has to verify his wallet address is real person or bot. Oh, cool. So this is really, really interesting use case. Okay. So for example, you could associate every wallet address with some data from their Web2 data. Okay. For example, I'm telling you, this is like, this is an example that we did in Reclaim basically is we associated every wallet address to their Web2 usage, and that to like zero knowledge proofs. For example, uh, if you want to know, like generate a zero knowledge proof of their maybe Swiggy order history, if they have ordered some food on Swiggy. So that is like, what are the criteria that you would define that a person is not a bot? So a person is not a bot. What criteria should they fulfill? They should have some kind of maybe Amazon order. They have placed Amazon order. They have placed Swiggy orders, or they might have some Twitter followers with some number of followers, threshold followers that you could use. That if someone has this many followers, okay, fine. That means that person is not a bot. Okay, so now what you do is you create a zero knowledge proof of these things, like if the zero knowledge proof of the Swiggy order history, zero knowledge proof of Amazon order history, and zero knowledge proof of the Twitter number of Twitter followers, and then you attach these proofs to the wallet address, and then you will get to know that if this wallet address belongs to a bot or to a person. And then what is the benefit of it is, next time when this wallet is being used, or if next time if this wallet is trying to do some transactions, you would know that if this is being done by a bot or some real person or whatever. Yeah. And this also can be used to for social recoveries. This is a very good topic, and I can take a session on that as well. Like, yeah, so that is how you can do it. So, Atul, did I answer, or do you have any other doubt? Okay, cool. So moving ahead, we'll talk about, so what we saw, the one example that we saw right now, the ball swapping example, that is an example of an interactive zero knowledge proof system. Okay, where the verifier and the prover, like both of them, like constantly talk to each other. The verifier is asking question to the prover, hey, answer me this, answer me that, like blah blah blah, like few rounds of conversations that goes on between the verifier and the prover before the verifier can come to the conclusion that the prover is right. Okay, so that is an example of an interactive zero knowledge proof system. There is another class of zero knowledge proof system, that is non-interactive proof systems. So what happens in non-interactive proof systems? So all these round of conversations that you saw right now, these get eliminated in non-interactive zero knowledge proof systems. So now let's see more characteristics. Okay, first let's talk about what are the problems with interactive zero knowledge proofs. So as you saw, so it requires two parties to be available, to be online at the same time, right? And they need to interact repeatedly, right? And the knowledge gained by the verifier of the proof submitted by the prover to the verifier, this proof now cannot be used by another verifier or another person. So now this person has to always generate a new proof and send it to the verifier, go into that, be a part of that conversation before their proof is accepted. Right now, this is such a huge task, right? For example, I am trying to prove to you that I am like maybe verify my age. I have to be online with you and constantly get on the conversation. So this is hectic, right? And so that is why we move to like non-interactive proof systems. So so one of the example of the non-interactive proof system is zk-SNARKs. So what is zk-SNARKs? So zero knowledge, as we saw previously also, that the prover can convince the verifier that they know something, they know the solution or something, without disclosing the details of the value or solution. So the verifier learns nothing about the actual data. Okay. Another property of ZK snarks is succinctness. What that means is the proofs generated during these non-interactive sessions are like very small size. Okay. And that makes it very compact. And also this helps in quick verification of proofs. Okay. Because of this, because of their like smaller size. Next, obviously non-interactive. These are non-interactive, as in the prover who wants to prove something, they generate the proof only once. They can share the proof with anyone they want to, and whosoever wants to, like, verify this proof, they can verify it independently. That is public verification of the proofs. Okay. For example, I generated a zero knowledge proof for my age only once, and now I can share it with all of you, and all of you can independently at your own time, at your own pace, can now verify my proof. Okay. So this is what the beauty of ZK snarks are, basically the non-interactive proof systems. Cool. Let's move ahead. Cool. So I think I really recommend that let's watch a video on how Reclaim has applied this. That will make things more clear, because all talks, like, people have been discussing about zero knowledge proof and whatnot, but it's important to see how things are implemented. So let's watch this video.
In this video, I'm going to be explaining the basics of how the Reclaim protocol works. Consider two parties, Alice and Bob, where Alice wants to prove some fact to Bob, for example, that she has $100 in her bank account. If she makes this claim, the problem is, why should Bob believe her? There are a few different ways we could try to tackle this problem. For example, Alice could give her banking password to Bob. That's not very safe, because if Alice tells him her password, he can verify that she has $100, but he's also able to access the account and take the money. Alice could ask the bank for her data. And on the internet, that looks something like she sends a sealed request to the bank. The bank sees the request, sends a sealed response. Alice can open up the response and show Bob that it says that she's $100 in her account. But Bob is not able to verify that the letter actually came from the bank. For all he knows, Alice could have just written it herself. So this is where Reclaim comes in. Because Reclaim lets Alice prove where her data came from using what we call a tester. A tester is another party that sits in between Alice and the bank. When Alice sends her request to the bank sends the response to the attester, who then signs off that they saw that the letter actually came from the source Alice is claiming. The attester then sends the response over to Alice, who can open up the envelope, show Bob that it says she has $100 in her account, and also that the attester signed the outside of the envelope, so it must have actually come from the bank, as long as Bob trusts the attester to be telling the truth. If Bob doesn't trust a single attester, multiple ones can be used with an economic mechanism where if one is caught being dishonest, they're penalized. So what this looks like is, say we have a set of 3 attesters now. Alice sends a request to the bank as before. The bank returns the response to all of the attesters, who each individually observe where it came from and sign off that it came from the correct source. The response is then passed on to Alice, who can show the contents to Bob as well as the signatures of each of the attesters. Secondly, Reclaim lets Alice only show the parts of her data that she chooses to show. So in the bank response, for example, it might show additional information than just that she has $100. It could also say what her address is, which is not relevant to what she needs to show to Bob, and she would prefer to keep private. So using a zero knowledge proof technology, she can redact the parts of the data that she doesn't want to share, while still showing the correct data in a way that Bob can trust. So now the redacted data just says that she has $100 in her account. Thanks for watching.
Yeah, I hope anyone has any questions on this. Like, did you folks were able to get what it is doing? So basically, there are two people, Alice and Bob. Alice wants to verify to Bob that I have certain amount of money in my bank account. So in the first case, what can be the first way of doing it? Like the most naive way. Alice can share her banking credentials with Bob, and Bob can themselves check the bank account if she's having that much money, right? But that is not a very safe way to do it, because right, like Bob can transfer the money in their account. So we are not supposed to share credentials. so now what comes next? Okay, so what Alice could say is, okay, fine, I'll give you something that I'll ask the bank to, hey, bank, just send me something that I could show to Bob that this bank statement is coming from your website, okay, and not from anywhere else. Okay, so yeah, so what Alice would say, hey bank, send me some kind of statement, and that I can show to Bob that these statements came from your bank and I'm not fudging. Okay, fine. She logged into her website and bank. So what I'm telling her is it happens below the protocol. It works under like TLS layer, what I'm talking about. So I'm giving a very, very brief overview of what is happening. So now what Alice did, Alice is talking to the website, telling the bank website, hey, logged into it, and told, hey, give me some response that I logged into your website and this is the data. Fine, bank gave her the statement that, hey, Alice logged into my website and this is the data that she accessed. Fine. Now she took this and gave it to Bob. Now Bob is like, hey, why do I trust you? How can I trust that this envelope that contains the statement from the bank is really from the bank, right? How will Bob agree to that? Like, how will Bob verify that? Okay, fine. So what Alice did, okay, fine. What we will do is we'll have some kind of attesters, right? In real world also, when we try to submit some documentations, you remember, right? We have to get it attested from some government officials. Even if you do like take some Xerox copy of it, we go to some gazetted officer who signs on it, like attest it that yes, that Xerox copy is correct and this was like taken from the my bank, right? For example, if you go for visa and all, you sealed copy of your bank statements, right? That is kind of a attested. Okay, but same thing is now happening in the HTTP request response thing. Okay, now Reclaim has introduced an attester that signs basically that your data that you're telling Bob that it belongs to you is coming from the correct website, like legit website. And the Reclaim node, basically the witness signs it, that you can share it with Bob. Now the thing is, when you share this statement with Bob that you have this data like $100 with this, like everything on your statement, like bank statement, now goes to Bob. But now again, you can choose what information you want to show to Bob. For example, you don't want to show that what is your address, or you don't want to show the exact amount of money that is in your bank statement. Now what Reclaim also provides you this option that you can create a zero knowledge proof out of it. And then now when you share it with Bob, you only share the zero knowledge proof of this amount of data is there, like more than $100 is there in my bank. Okay, so this kind of thing is possible with Reclaim and with due diligence to zero knowledge proofs. That is what zero knowledge proofs enable us to build. And yeah, so this is one example of Reclaim that is built on top of zero knowledge proofs. The world is vast, and the scope is way big of coming up with next applications of zero knowledge proofs. Won't the auditor know Alice info if they verify, then how will it be private? And here, so Bob can verify that it's coming from the bank. Okay. Won't the auditor know Alice info if they verify it, then how will it be private? So basically, the auditor doesn't get to see Alice's details. Actually, they don't get to see Alice you, if you're referring to username, password, or some secret information, cookies or anything. No, they don't get to see that. So yeah, I would tell you, I would recommend study, maybe you could go back and study on more TLS protocol. Basically, there's a method called key update. You can visit Reclaimka white paper also, where it's written, everything is written, like how this preserves the privacy of the user. Yeah, so these are the things that is possible using zero knowledge proofs. And you can download the Reclaim app if you want to check it out, if you want to create zero knowledge proofs on your phone. Right, so Reclaim app does. Oh, so yeah, oh yeah, I can get that. But in those cases, right, we need to change the bank. We need to tie up with bank, right? Hey, bank, we need to go, for example, ICICI Bank or some bank, and go and talk to them and establish this kind of a thing. But going to each bank and establishing that kind of a protocol that you give this kind of a copy is cumbersome, right? So we want to make a more permissionless ecosystem. Breaks decentralization. How breaks decentralization? I'm not that clear about it.
I think the idea is like you generate a proof in a way that this this asset, the third party, who's this middle person, this auditor, can
Yeah.
and attest to it that this proof is like correct.
Correct, yes.
And then you just use that proof to basically you can use that proof anywhere else, I presume. Like for example, I think this is like you need to take the bank statement of the of every bank wherever you want to create that proof. So I think bank thing, you will still have to go to every bank to be able to get the proof. Sending this digitally signed letter seems like what this person in the auditor is doing, I believe, right?
Yeah, kind of. Yeah, they audit it, like if the request and response belong to the same server, coming from the same server. Yeah. Rohit, yeah, actually Rohit is right here, going to banks and asking for the permission. Yes, this is very really interesting. If you want to try it out for yourself, you can just download a Reclaim app and you will get to experience it for yourself. Like you can create proofs of your all the accounts, I mean whatever you want. Cool. Now moving next. Yeah, now it's time for some hands-on sessions. Let's do it. It won't take much time and it's very basic. Many of you might know already these things, but let's do it again since we are starting the ZK month. We're writing the circuit first of all. So let's open our VS Code. I'll open my VS Code as well. Okay. Is my VS Code visible to everyone?
No, Sweta, only the circuit has become small.
Smaller. Okay, cool. Wait. I'll just. Let me do something. Screen share my screen. Cool. Now I think it should be visible, right?
Yes, it's visible now.
Okay, cool. So I'll just quickly create a new folder, maybe ZK month. And open it up. I trust the authors. Okay, fine. The author is me. So I'll quickly create a new project, that is npm init-y. This will create a new project for me. Next,
For
what?
everyone who's following along, I added the prerequisites that Sweta sent a while ago, and I'm just copy pasting the prerequisites again. So basically, yeah, you need like Node and Circom installed. And if you have Windows, then I recommend spending some time to install WSL2 because it's honestly makes your life really easy if you plan to program not just in Web3 but in any web. It's much easier to have a terminal based operating system. So yeah, even if it takes a while, I would recommend installing WSL2. And then if you have you need to install Node on top of that as well as Circom. So yeah, sorry Shweta, go ahead.
Yeah, sure. So first we did npm init-y. This will initialize our project. Mac user, uh, same. I mean, you can just follow along.
Yeah, you just install Node.js and Circom and you should be good.
Yeah. Next, we will be installing circomlib. I will put it in the chat as well. So basically, this library will expose us to the few functions that will be needed while writing the circuit. So we will just install circumlib and let it install. Cool, and it installed. Next, what we will do is we will be writing the circuit. So what the circuit will do is it will take an input and it will output a signal. Okay, so there will be only one single input and only single output, and this input will be giving to a Peterson hash, like we'll be creating a hash, and kind of you let anyone to prove that they know some secret value that belongs to a hash, like this hash is formed from this secret value, but they won't ever reveal the secret. They will just know that they know the value that was used to generate the hash, basically Peterson hash. So we'll quickly create a file called maybe circuit.circom. Let's do it, circuit.circom. And first what we'll do is we'll do some pragma circom thing that okay, sorry. Yeah. So what we did is first we did npm init-y. That is, I'll just post it here, npm init-y. So this will initialize your project. After you do npm init-y and your project is initialized, what we will do is we will install this library called circomlib that will enable us to write circuits using circom. Okay, you can read more about circom. Wait, let me share the link to circom.
Shweta, can you introduce Circom for just 1 or 2 minutes? Just
Oh,
tell
yeah.
what is Circom, like what do people do with Circom?
Cool. So circom is basically, it's a compiler and that enables you to write circuits in the circom language, basically. Yeah, and this language circom, it provides you, basically when we create proofs, it requires us the circuits and all the constraints. Basically when we create a proof, it requires everything to be in the form of like logic gates like and or and all those stuff. But circom, it abstracts away those stuff and enables us to write our proving logic, like to generate the proof in a way that is more user friendly, basically. So for that we require writing circuits that enables constraints that is used to create proofs. Now writing circuits can be done in there's one more called, I'm not remembering the name right now. So writing circuits can be done using circom language, or there's one more called Socrates, I think, Socrates.
There are multiple programming languages that have come up, but the idea behind writing these circuits is actually, so when you create a proof, and we have another talk by Ovia which will happen in a bit later timeline, which will talk about the mathematics behind snarks. And then we also have a talk which will talk about the mathematics behind Starks. So every different type of algorithm has a different mathematics to it. But the overall idea of how zero knowledge proofs are created is that using these mathematical algorithms, you will create an equation. And then you will have some constraints that you will put into this equation. And you will check whether this equation is giving the desired result or not. Basically, the equation should result to zero. So something like if it is x minus 1 into x minus 2, which is a polynomial equation, you will use the constraints like 1 and 2 as a verifier to verify whether this particular equation is leading 0 for 1, is it leading 0 for 2. If it is, that means the proof is correct. And if it is leading 0, if it is giving 0 for any other value, that means the proof is invalid. So as a verifier, you can also check the completeness. That is, for both 1 and 2, it should give 0. Then only it's complete, not for either or. And then is it sound? That means if you give wrong values, is it still accepting? So if you give 3 or 4 or 5, is it still giving 0? No. And then zero knowledge. That is, the way you pass these inputs, right, to this particular circuit, it should be private. That is, external people will not know about this input. And these are the three properties that this mathematical equation. So don't go with x minus 1 x by into x minus 2. It's just a simple thing that I told just to make sure that you understand. But there will be a mathematical equation and there'll be a set of constraints that will be applied on this mathematical equation. Now, this entire constraint system is built into different types of programming language in which you can write this constraint system. Basically, computer science is nothing but taking mathematics and writing it in a language that the computer understands, right? That's the science of computers. You take the mathematical equations and you give it to the computer and you make sure that the computer can compute these equations faster than humans can. So you take these mathematical equations and then you give it to the computer, and to give it to the computer, we have this programming language layer. So in this case, Circom is the programming language which you will use to write circuits which will follow this constraint system, and it will allow you to create logic so that you can prove anything XYZ. So now Sweta has given a particular logic that a person can prove that they know a number or something, whatever that might be. So for different problem statements in Circom, you have to write different types of circuits. So that's what she's going to be teaching about, that how do you write your circuits actually and generate a proof using Circom.
Yes, exactly. Thanks, Yan, for like the beautiful explanation. Now moving ahead, we'll be writing the circuit, and first we'll be defining the compiler version. And we do it this way. We write it using Pragma Circom. Like I'll just post it in the chat as well. This is the way we, if you're familiar with the Solidity as well, there also we write some compiler version that this circuit should use. Next, we'll be importing the Pedersen circuit. Pedersen circuit is basically, it enables us to, create a hash of anything. Pedersen hash, basically, it's a way of hashing something. It's a different logic. So yeah, so this circuit will enable us to create a hash of the secret value. Okay, we'll import that, and then we will, okay, my GitHub Copilot is already telling me what to write. Pedersen hasher will now create the circuit basically. And yeah, so this is how we define the structure of a circuit. I will put this in the chat as well. Okay, now we will define the input. So our first input, so these inputs are called signals, and we will tell this input, name this input as maybe number, or say in, okay, or secret number. Okay, so this is some secret number that only I have access to. And now what I want to prove that I know this secret number, and I will do a signal output hash. that the output of this circuit should be a hash value that I know, and this hash, it will be a public signal that anyone would be knowing. Now what we'll do is we will call this Pedersen hasher. Okay, copilot. Yeah, so we'll call this Pedersen from this library that we just imported. And what it will do is it will hash the value. And what value should it hash? Like we will use a Pedersen hasher with only one input, because we have only one input to give it. And now what we'll do is we'll pass in to the first input to. So this is how we pass, value to the Pedersen hasher. Like we are passing the secret number to the Pedersen hasher, and what it should output is the hash basically, and we'll hash should be equal to Pedersen.out. So whatever output, so what input we are giving to the Pedersen function, we are giving the secret number, and it is giving us Pedersen output as the hash. So this is how, like, it's reverse here. Here right side, like we assign value in the left hand side, and the function is like the right side. So now this is a circuit. What it does is it will take a secret number and it will output a hash. And how is this hash calculated? It is calculated using the Pedersen circuit. Okay, now we need to expose this component, and we expose this component using like something called main is equal to Pedersen hasher. Okay, so now our circuit is done.
Can you explain the keywords a little bit, Sweta? The template and the component and all. Like when should we use what? In case we want to. In case people want to start writing their own circuits.
Okay. Just a minute. Yeah. So yeah, what this does is templates are like reusable components. Okay. So these are reusable circuit components that can be used by you anywhere. Okay, for example, here what we have defined is a Pedersen hasher component. And if we go to this, we are able to use Pedersen component here because this component was written inside the Pedersen.circom file. So in the similar way, when you write this as template, so what you make basically is you are making a component here that can be reused by anyone. Okay, for example, here we are creating a main component and we are assigning Pedersen hasher here. Now main component can be used by you anyhow. Okay, in the same way, Pedersen component was made here, like a template Pedersen was written inside Pedersen.circom. You can just go to node modules, and inside node modules there's circumlib circuits, and you will be finding some Pedersen circom. Okay, so here is again a template, and like it's a very long thing. This it is because of these templates that it becomes reusable for it makes the circuits reusable basically, nothing else. Cool. So yeah, and that is what is about template. Next is signal. So in circuits, in circom, signals represent the data inputs or outputs. Okay, so for example, like in other languages we have variables like var, int, something of that sort. Here we have signals that defines that this is a data input or output thing, like it can be public input or public output. Okay, and then what we have is this is like just calling the Pedersen from this component, like Pedersen component, and that what one signifies over here is that we will be passing only one value to the Pedersen function, and then we pass secret number that we defined here, like the value that we'll be passing here to the one input to the Pedersen, like the first input to Pedersen function, and then whatever is output by the Pedersen function, we store it in the hash variable. Okay, so now this secret number we will be passing this will be passed by the user. Cool. So now once our circuit is done, we need to compile the circuit. And for compiling the circuit, you might have installed Circom in your laptops, I mean system, that Gyan had shared in the chat. So if you have already installed Circom in your laptop, you could directly do, wait, let me share it. You can directly compile it using Circom, circuit.circom, R1CS and WASM. So what it will do is it will compile your circuit. Assign types does not match. Okay. Sorry for that. Oh, okay. We need to. So since we gave the secret number to the first input, we need to output the first output. Yeah, sorry. Yeah, so now what we'll do is we will compile the circuit, and what it will do is it will generate two files. One is R1CS file, another is the WASM file. You will find this here, circuit.r1cs, and where is that? Circuit, yeah, so WASM files are inside this. So what it will, so this is like very high level overview of the circuit, but the proof system, the ZK snarks need a mathematical system, right? The language in a very mathematical form and very low level form, and that is where R1CS comes. This what it does is it represents this entire circuit in a form of mathematics, so in a more logical mathematical form. So that is what R1CS does, and this is what will be used for verifying and generating the proofs. So now that we have compiled our circuit, next step in any ZK system is to form a trusted setup. Now, this trusted setup means that many parties come together and agree to a particular setup and generate a like power of tau file. Okay, so we are not engaging in that. We already have some pre-generated power of tau file available that anyone can use it for the testing purposes at least, but not for production. So right now we will be using that file. You can download it from here. I'll just share the link. You can, that is hosted in Amazon S3, and you can download it from there. I'll share it in the chat. Yeah, so you can just use this command if you are on Mac OS to download this file, or if you're on Windows or anything, you can just use this S3 link bucket link to download the file. Okay, so once you've downloaded the file, okay, I also need to download. Yeah, so I'm just downloading the file. It is getting downloaded. So what is this file required for? So this file, so when we perform so this file is basically, it will be used for generating the proving key and the verification key. Okay, now what is proving key used for? Proving key is used by the prover to prove their proofs, and the verification key is used by the verifier to verify the proof that will be generated. So is everyone with me? Like, did you folks download the power of tau file? Could you please share in the chat, like if you are with me? If you have any doubts still here, or if you have anywhere, if you're stuck, just feel free to maybe unmute yourself and talk, or post it in the chat. Like, we will help you.
Yeah, I'm answering a few questions, like what are components and stuff. Justin says that he has downloaded the Powers of Tau file. For those of you who are like little bit confused, don't worry. Some of these terminologies we will talk about in depth in the
Yeah.
but this is to, like, basically the idea of this is for you to understand that actually creating zero knowledge proofs is not that difficult.
Exactly.
It's very easy. It's like very straightforward.
Mm.
You need to learn a little bit of circom. Obviously, if you're going to use snarks, then you have Cairo for Starks, and then you have different programming languages. So whatever suits you best, and what kind of applications do you want to build in which line and stuff like that. All of that matter, of course. But just building like learning to write circom and stuff like that is not that difficult, especially if you are a computer science engineer and are familiar with some programming language. So the idea of this session is that all of these terminologies like powers of tau, which is the trusted setup ceremony, and the CS, everything will be explained in much more depth in the mathematics theory session. But you don't actually need to go that depth in it right away to start writing the circuits. There is error, Shweta, warn tar entry invalid base 256 encoding.
How are you trying to download it?
Atul, can you?
What were you trying to do? Basically, that may like when you face this error. Installing, like what are you installing?
Installing npm or circom? Oh,
Oh, okay. This is weird.
Yeah, it's just a file, Atul. So you should be able to just download this file. There is no installation associated with it. It's just a file that contains some sort of random numbers.
Yeah.
So you see, like this, it's just a file. So why is it asking you to, why does it think it's a tar file? It's not a tar file. It's a, you don't have to install it. Don't click on it. That's why it's trying to
Click on
do this
it.
error.
Yeah. Don't click on it.
Yeah, just install and store it in a folder.
Yeah. Just, I mean, download it. Yes.
That's it. Yeah. Just download and store it in a folder.
Yeah.
So, sorry, no installation. That's
Yes.
why it's trying to find out whether it's a tar file. And then it is saying, no, it is not a tar file. So I'm not able to, open it up and stuff. Yeah, no problem. Okay. We are good. So,
Yeah. Cool.
Nanda Gopan, are you are you good? Have you been able to download? I think you were actively also following up with the tutorial.
Yeah, I was actually following. I did not download it yet. I'll try it. I'll try right away.
Okay. Yeah. Okay, Shweta, I think you can move forward if you want, like just to.
Okay, cool. So I think I'm seeing a few people have joined right now. I'm just writing it in the chat, like what all we did. We just initialized the project with npm init-y. We did something called installation of circumlib that would help us in writing the circum circuits. Basically, yeah, so we did these two things, and what we did is, so okay, let me just recap once more so that everyone is on the same page. We initialized the project, and then we wrote the circuit. This is a circuit that takes in a secret number that only the user knows, and the user wants to prove that they know some secret number and that the hash has been generated from that secret number without even revealing the secret number. So what anyone could see is the hash, and yeah, that's it. Okay, and this is a circuit that we wrote, and then what we did is we compiled the circuit. What we did for compiling the circuit is, what happened to my download? Done. Okay, cool. And then what we did for compiling the circuit is basically run this command, and what it does is it basically let me show in the chat again. So we basically did this. What it does is it generates two files, basically R1CS file, that is the file that contains the circuit in a more mathematical terms, basically mathematical representation of the circuit. And this R1CS file is the file that will be used in creating the proofs and verifying the proofs. And now for creating proofs and verifying proofs, we need two keys. One is the proving key, another is the verification key. Now, how do we generate this proving key and verification key? So for doing that, we need some kind of a trusted setup and some ceremony and all that needs to be done, but we will not do it right now. We will just use the one which has been done from before and is publicly available for anyone to use it. So we just downloaded the powers of tau file from Amazon, and yes. So here is the command to download this file, and you can download this file if you're on Mac OS using this link. Cool. So now moving ahead, now we have the two files. Okay, were everyone able to compile circuits? Were everyone able to compile their circuit? And these files were generated. Are we on the same page here? Please comment on the chat, like if you are on the same, if you are on the same page, please mention yes, no, whatever, so that we can move ahead. We're just one step away from creating proofs and verifying proofs. That's it. That's how easy it is. So the main intention of doing this hands-on is to like tell you that it's not a rocket science thing. Under the hood is rocket science, but creating a simple zero knowledge proof system is not a very big thing to do. Like you can do it, and yeah, it's always better to learn about what goes inside it, like the mathematics that I think Ovia will be covering, and even I would like to learn more about what's the mathematics that gets inside it. Cool. So now moving ahead, what we'll do is, now since we have the two files, we will generate the proving key and the verification key. Now, how does that happen? So for that, we need to install Snark.js, okay? So that is where Snark.js comes in. Now we will be installing Snark.js, that is npm install Snark.js. Cool, so just install Snark.js. And yes, Snark.js has been installed for me. I hope it has installed for everyone else here. Cool. So after installing Snark.js, what we will be doing is we will be using Snark.js to generate the basically proving key and the verification key. Now to generate the proving key and verification key, it requires our circuit. Okay, so what we'll do is we'll do npx snark.js, and we will pass in grot16. But grot16 is basically how the way proofs should be implemented. That is the algorithm basically that will be used to generate the proving key and verification key. There are a lot of other algorithms as well, but grot16 is the most, I guess, the followed one and the most stable one, I guess. So we'll be using grot16, and then we'll set up the circuit dot R1CS. So remember the file R1CS file that we generated just before. We compiled the circuit and we generated the R1CS file. So we'll be using this file to generate the proving key and the verifying key. And what we'll be using is the R1CS file and the powers of tau file that we just downloaded. Okay, and then we will name the file that will contain our proving key and the verification. We'll name that file as whatever you want to call it, circuit key, maybe circuit key dot zkey. This is the extension that is used for storing the proving key and the verification key. And now enter. Hopefully it should generate. Okay, cool, it generated. And I'll just share this command in the chat as well. Cool. Yes, this is a command, and then you will see that it generated something called circuit key.z key file that contains the proving key and the verification key. That this key was generated using the powers of tau file and the circuit, the compiled circuit. Okay. So now once we have the verification and proving key, the next step is to generate a proof. Now we will see this in action. For example, any user should come in and they should be able to create a proof. Now I'll do some index.js. We'll create a file called index.js where we'll be importing snark.js that will be used to create the proof. So this is how you will be importing snark.js. Now we will write a function called generate proof. We'll write a function to generate proof basically, and it is telling me this. Okay. And what we'll do is we will do basically, so we will be using Stack.js library to generate a proof. Okay. So how it is done is we will be doing what here it is showing. Unexpected finding. Okay, sorry. Yeah. So now what we'll do, we'll be using Stack.js to, we'll be using groth16 because we used groth16 to generate the verification and proving key. And then we will be do full proof. And we will, it will take as input the secret number that only I know. Now, since for this demo, you all know as well, maybe the secret number is say 25. So this is a secret number that I want to prove. And what I want to do is, it also takes input as the wasm file that was generated. Okay, so the wasm file that was generated is inside this circuit underscore JS folder. If I go into circuit JS folder, there is circuit.wasm file here. So we need to use this file. So this takes an input the wasm file and the keys that was generated, the proving key. So the proving key resides under this circuit key dot z key. Okay, so the proving key is residing inside this file called circuit key dot z key. That is why we have passed this file, so that this the proof should take the proving key from this file. Okay, fine, we are done over here. Now what we'll do is, what is the output of this? What is the output of this function? So the output of this function is a proof, right? Because this is what we are doing is we are generating a proof. So it will generate a proof. Okay. And what it will generate is a public signals. Now, what are public signals? Public signals are basically the inputs or the signals that can be used by, for example, for us, the public signal was the hash, right? When we created the circuit, this was our public, the output is hash. Okay. So these are the public signal that anyone can use to, like the verifier will input the public signal to the circuit, the hash and the proof, and they will able to verify that the hash was correctly generated using the proof. Okay. And then the verifier will get to know that the user knows the number. Okay. So now what we will be doing is we will call this function called generate proof. And we'll say proof generated. And then what we'll do is we will just exit. What is this? Did I miss some bracket? Okay. Cool. So I think we are good to go. Now what it will do is it will generate a proof. We can do a little console log also. Let's do some console log. Okay. Let's do console log of the proof and the public signals. Let's pray that this works. Cool, let's see. Now to run it, is everyone on the same page?
Does anyone have any questions? This
Yeah.
is just a simple like JS file. So you are creating, that you're just creating a JS file and you're importing a library and just trying to generate a proof. So it's
Yeah.
quite straightforward. But if you have any questions, feel free to drop them as well.
Every other developers, yeah, right. So hopefully it should run, or else if any error will debug, not a big deal. So let's do node index.js. Okay, it did throw some signal not found. Okay, secret. Okay, sorry. So this number, so this variable should be the same. I just use some different number. Yeah. This variable name should be same. Okay, so the one you put it in the circuit, it should be same. Hopefully it should run now. Okay, a proof is not defined. Okay, wait. Move this outside. Cool. अरे यार.
It's because
Okay.
proof is inside
Yeah,
that.
okay, yeah, got it. Yes, so the proof is generated, and so here we have the proof. Okay, so this is what the proof looks like, and this is the public signals. Cool. So now that we have the so see, we just created zero knowledge proof. Wow. So this is not that yeah, I know. So it was not that a very, people fear about it, how to do it, how and what not to do it. So this is really simple, and just now we just created a zero knowledge proof of the based on the circuit that we created. So to be really honest, the real thing that we need to learn is how to write the circuits, because most of the knowledge should goes there, like how to write a very secure and a circuit that follows all the three properties of zero knowledge proof. That is where the competence lies. And so this is what we did right now, is a very simple circuit, and we just created a zero knowledge proof out of it. Now what we want to do, okay, so fine, the proof is created. Now we want to verify it as well, right? Now you can give this proof to anyone and they should be able to verify the proof. So let's now write a verification function as well. So for verification function, okay. So now to verify, this proof, okay, so basically if you, so in the last lecture, session, we covered about asymmetric public key cryptography. Okay, so there is some private key, there's some public key, and using the public key you can just how that works. So here the proving key that we just generated, okay, we need to also generate a verification key that was used from the proving key. Basically, the proving key that we generated and it resides under this Z key, we will be exporting the verification key that can be used by anyone to prove this circuit, to prove the proofs that was generated using this circuit, basically. So what we'll do now is we will generate a verification key as well, like basically export the verification key from the Z key. So how to do that is we will just run npx snark js and Z key export, and what will we export is verification key. From where should we export the verification key? Now, why we are doing this? We are doing this so that anyone can verify this proof, right? This verification key should be available to anyone who wants to verify the proof. Okay, so for that, what we'll doing is we'll be using the file that contains the verification key, basically circuit, what is the name? Underscore key dot z key. Yeah, this is the file that contains the verification key, and we will export it in a JSON file. Okay, that can be used by verification key dot JSON. So this file contains the in this file the verification key will basically be exported. Hopefully it exports. Export verification key started. Okay, yes, it exported the verification key. So I'll just share this command in the chat basically, and here it is. So you can just use this command to export the verification key, and this key is stored in the JSON file here. So this is basically the verification key that we will be using to verify the proofs. So now what we'll be doing is we will create a new file called verify.js. Okay, that so the task of this file is to take any proof and verify that if the proof was correct or not. So what we'll do again is we will import snark.js. We'll import snark.js is equal to require snark.js. Yes, right. And what we'll do is we'll create a function called async function, it's called verify proof. So now what this verification of proof. So previously we did a generate proof function. Now we'll do a verification function, and what it should do is, okay, in this function, basically we'll generate the proof here only, because, you know, for the sake of demo purposes, we'll generate the proof first and then use it to, we'll first generate the proof basically. So what we did is secret num, and then what we did was what did we pass? We passed the wasm file, and then we passed the key file using which the proof will be generated. And then what it returned was proof. It returned us the proof and the public signals, right? So, and yeah, so once it returns the proof and the public signals, now anyone can use it to verify these proofs. Okay, and how to verify that is we will use the verification function await snark.js dot growth. Okay, and dot verify. So what we'll do is we will use this thing. Okay, now verification function would require the verification key, right? So we should first import it. So we should import the verification key is equal to from this file called verification key.json file. So for that, we would need a file system library that is fs. We can use this to read the files basically from the system. And then what we will do is we will do a fs.read file. Okay, we'll try to read the file called verification key. Verification key underscore key dot JSON file. Okay, so we will try to read this verification key dot JSON file, and I think this is not needed. We'll just remove it. Okay, yeah, we'll read this file, and then what we'll do is it will be read as a string. Okay, so we will just parse it as JSON file. We'll pass the entire file as JSON so that we get a JSON the key in a JSON format basically. And then what we'll do is we'll pass this verification key to this verification function. And how do we do it is we will just pass the verification key and the public signals to the verification function and the proof. Okay, so the verification function requires three things: the verification key, using which it will be able to verify the proof, and the public signals. Public signal is basically the hash value that we defined in the circuit. Okay, this is the public signal. And yeah, the secret number, we are not showing the secret number to the verification function. And where is this? Yes, so right now we have this in place. Now what we'll do is the verification function should return some result. Okay, so it should return some result. Cool. Now what we'll do is if result is true, okay, now result is a Boolean value. If result is true, the proof is valid, else what it is, the proof is not valid. Cool. So this is a very basic proof generation and verification function. So here we are generating the proof inside this function only. But when we will be building, like if you're building your own application or something of that sort, you can like put this function, the proof generation function in the client side code, where the proof is actually being generated, and the verification function may be some other place where the person who wants to verify it, that way you can structure it in your application based on your requirements, based on the business logic. So now we have the function ready. Okay, now it's the time to verify it. Hopefully it runs again. let's do it. So node verify dot verify.js. Okay, fingers crossed. It should let me check once more. I'm just writing live, so I don't know if it will, how can you verify on chain? Oh yes, so this is, Ovia will come to your question a bit later, like after doing this. So let's run this and see. Oh, we didn't call this function, sorry. My bad, we didn't call this function. Verify proof, okay, then proof verified. Yes, and then yes, so we have called this verify proof function, and we can, okay, proof maybe verification complete. Cool. Okay, chalo, let's run this. Oh wow, the proof is valid. Okay, so you can see my logs, right? The proof is valid. So what it did is, so it just received the proof and just used that proof only to this verification function, like snarkjs growth.verify, this method, and it passed the verification key and the public signal that was an output of this like generation of proof function, and it correctly like identified that the circuit, like the hash was generated using this circuit, and it said that the result is true and the proof is valid. So what we can experiment with is, maybe we can just add some dummy value in the proof and see if it is able to detect it. So that would be a fun exercise actually, that you all can try in your free time when you're going through all this. So what we did right now, like, could you just imagine, like, we just created a circuit which generated proof using snarkjs, zk snark, and then we were also able to verify the proof. Cool. So are we all on the same page? How many of you just did this? I'm really excited to know.
I think few people were following along, but
Okay.
got stuck here and there. But probably they can watch the recording incomplete. And
Yeah.
whatever part you have left, Shweta, if you can share a small text on that, then we can give that as a homework.
Oh, okay. Cool. Yeah. Can you know what the difference intermediate files were? I didn't I didn't get you, Obia. Like, what are you saying?
Like the different JavaScript files, Ovia, which are the, or maybe just go through the files that are there as part of your directory.
Okay. Sure. I'll just do it. Okay. So basically, okay. So index.js file, like, so this file was just generated for demo purpose of like creating proof. This was just to demo that how to write the code of generating proof and the public signals. Okay, that's it. Next, we created a verified.js file. What it did was just to, since what it did was that it generated a proof here, the same thing that we did here, basically. Okay, same thing we did here. It generated the proof and public signals. We used that proof and public signals and sent it to the verification function. Okay, right? And then we like we got the result, we stored the result in this variable called result, and then we checked this, that the result is true or false based on the verification was valid or not. Okay, just that.
Sweta,
Uh-huh.
can you hear me?
Yeah,
Yeah,
I can hear
I
you.
meant like from the beginning, right? When we created that circuit.circom file, and then when we compiled it, we got two files, R1CS and WASM, right?
Yes,
I want
yes.
to know what those are, and then again then you use this powers of tau file, and then you create so I just wanted to know what, and that zkey file, what are these files? What are the steps of creating the proof, basically?
Oh, okay. Cool. So basically what we did was, so what we did is, like, first we created a like high level circuit, okay, using circom. Okay, so the proofs, okay, there are few chats also. Okay.
No worries. I'm managing the chats. Don't worry. Just-
Okay, cool. So the proofing, so when we give something to Snap.js, so if you saw here, that it was accepting a WASM file, okay, and then it was accepting something called zkey file. So these files are more written in terms of like in a mathematical terms. Okay, so if you just a minute. So if you check, so R1CS file is basically like binary representation of this entire whatever circuit we wrote. Okay, and since the computer or the like low level machine, like they understand like very binary format of data, so that is why we use the circom file to first create a circuit, and then we compiled the circuit using the circom compiler to generate these two files called R1CS file and the WASM file. These are very low level files. They represent the circuit, they represent this circuit only, but in a very low level format. I am just not remembering the full name of R1CS. That is something called rank 1 constraint systems file. Okay, so it represents this circuit in a more mathematical terms, okay, in terms of logic gates and in a more a cyclic graph kind of thing. So that is what the functionality of this R1CS and WASM files are. Okay, so after compiling the after compiling the circuit, we got these two files. Now we got the file, but then we need, what do we need is a trusted setup. Okay, we must have heard of this trusted ceremony being conducted to create this some kind of trusted setup and all. So we didn't do that. What we did is we used the already created trusted setup. Okay, that was the powers of tau file. To be really honest, I also do not have very clear idea on the mathematics behind the creation of this trusted setup file. Like, but what I know from my little knowledge is that this trusted setup, I think Obi, you would know more because you have better understanding of the mathematics behind it. So this powers of tau file is created so that people agree on some kind of agreements and security systems assumptions to create this kind of file, trusted files, that is used for generating the proving key and the verification key. Okay, Now, what we did is, after we got these powers of tau file, what we did was to generate the proving key and the verification key. Proving key, why proving key is required? That is required to create the proofs. Why verification key is required? That is used to create the that is used to verify the proofs. Okay. Now, how to generate this proving key and the verification key? So to do that, we did yeah. So to use what do I say? So now to create that key, we use that, so that is stored, the proving key and verification key is stored in this Z key file. Okay, so now this Z key file, how do we do it? How to generate this proving key and verification key? This proving key and verification key is generated using the R1CS file that we just compiled it. Okay, that is just the circom, that's just a circuit in a more mathematical fashion. Okay, this same circuit, but the representation is a more mathematical form. So it accepts that R1CS file of the circuit and the tau file, the p tau file, the powers of tau file basically, and it generates using this two a proving key and the verification key, because this key should have knowledge of this circuit, right? Because this proving key, these two keys are required to generate proof and verify the proofs. So this it requires knowledge of this circuit. So using this two, we generated the proving key and the verification key, and that got stored in the Z key file. Okay, this Z key file. Now this contains the proving key, and that is why when we were generating the proof, okay, when we were generating the proof using full proof, this calling this Groth16 proof, full proof function, we passed in the Z key file over here, because this is what this accepts. Okay, so if you see over here also, just hover over on the function, you'll get to see the Z key file name, right? It accepts Z key file name. That where is the this file is stored, so that it can extract the proving key from there. Okay, and then it accepts the WASM file. Okay, and then it accepts our inputs, the circuit signals, and this is the private, like a private signal that only I know. I mean, you know, the user should know. Okay, so full proof accepts three parameters. One is the input signal, second is the WASM file, another is the ZK file. Now the ZK file contains the proving key, basically. That is why it requires the ZK file. Okay, so yeah, so that is why we have passing the WASM file, the ZK file, and the inputs. Now we have generated the proof and the public signals. Now what these public signals will be used for? So now these are the public inputs that anyone can know. Okay, and for example, this hash, I will give you the hash, I'll give you proof, and then I'll tell you that I know some number that was used to generate this hash, right? So this is what public signals are. Now when we are doing the verification function, now when we are doing the verification of the proof, what we are passing is the verification key. So what we actually did is, we first exported, basically we extracted the verification key out of this key file. Okay, we just extracted that key out of this key file and put it in a JSON format, because this verify function, it requires what? See, it requires the verifier, like the verification key, who is the verifier, and the public signals, and the proof. Okay, that is Groth16 proof, and that is why we passed in the verification key, we passed in public signals that was generated when creation of proof, and then we passed the proof itself, just so that they can verify correctly if the proof was generated using this like circuit or not. And yeah, that is how we did the entire thing.
Hey, thanks a lot. That was very helpful.
Yeah, thanks. So even I won't say I have full knowledge about everything ZK. Even I am learning and in the process of learning. This requires very I'm really happy that we started off with this ZK month, because this is bringing everyone in the ecosystem together on a common dialogue where we are talking about it, right? And we're discussing stuff. And so this is very important, and I would really appreciate everyone to come up with questions, doubts that you have, because only then we will be able to discuss things. We will be able to, for example, I do not know the exact mathematics that goes inside few of the things that is happening over here. I do not know it, but if, for example, if here someone knows the mathematics and they come with how explanations of the mathematics behind it. So this is such a collaborative effort, like one learns something, one learns some other part, and then when we come together we discuss stuff, and then everything becomes a complete picture. Yeah, that's it. So would love to listen and have chats about what problems you faced, or what is the experience, what more you want to learn, everyone. Cool. And that's it.
Awesome. That's like, thank you so much, Shweta. I think we have covered everything from introduction to zero noise proofs to writing a circum circuit. I know it was a slightly longer session, but I think we need to, as we go deeper and deeper into Web3 tech and tech surrounding this emerging technology, we need to spend a little more time understanding it better. So thank you so much, Shweta. Yeah, Saurav also says thanks. Everyone got to learn a lot today. And I shared another simple homework as well, which is you need to write a quadratic equation. Basically, you need to write a circum circuit to verify a quadratic equation. See, the thing is, it may sound intimidating, okay, but at the end of the day, it's actually very, very simple, right? So you can, right now, you wrote a Peterson hash circuit. You don't even need to know about any of the hashings, just simple multiplication and stuff like that. Half the things I've already given away, but it's very simple. So definitely try it out. We'll send an email as well with the homework session. And once you have done the homework, do share the GitHub on Twitter with the usual tags, hashtag ZK month for TPG, and tag us at Phoenix Guild. Tomorrow, our upcoming sessions are so far in this order. We have one speaker coming tomorrow who will be talking about SHA 256 and ECC. She is a cybersecurity expert. She was the director of cybersecurity at ABB, and she's now a cybersecurity lead director or one of those top positions in Dell. So if you have any other encryption related stuff that you want to learn, please let me know on the WhatsApp group so I can ask her to cover that quite briefly. And we chose SHA 256 and ECC because the elliptic curve cryptography is quite common, and it's vastly used in a lot of algorithms, and especially ECDSA, which is used in Ethereum. So elliptic curve digital signature algorithm. So I requested her to cover that. And then SHA 256, because it's also, again, quite common. You use it in Bitcoin and all of these other blockchains as well. But if there's any other cryptography primitive that you want to learn, then this is a good time, because Mini is generally very, very occupied. But this time she decided to give us 1.5 hours. So we should make the most of it tomorrow. And then we have one more session on Circom, where we'll just explore Circom as a language and different types of circuits, how we'll write the circuits. That will be the next session, most likely on Monday. The speaker is yet to confirm, but it will be Monday, 9th October mostly. And then the same week, we have another session, which will be about Merkle proofs and semaphore. So you need to know Circom to be able to understand that session. And post that, we'll have a session on how to build your dApp using Circom and React.js. So this entire thing will cover everything in the Snarks arena. And then we go on to understanding how Starks work like. And then we'll explore a bit of protocol. So we'll keep confirming the sessions as the speakers come in. Yes, we'll share the WhatsApp group link over email. I'll share this small homework as well. And if you have any questions, feel free to drop it on WhatsApp as well. I want to thank all of the speakers who have been in the past with the Phoenix Guild, giving us their time and their knowledge, and especially Shweta today for this amazing session. And I hope that, there'll be further sessions. There'll be one session on the mathematics for sure. So don't worry about it, Shweta. You can keep all your questions ready for that. And I hope that all of you also hope to participate in the future sessions. And I'll see you soon, tomorrow, most likely. Yeah. Thanks, everyone.